In this lesson, we're going to look at a couple of geometric proofs, starting with some two-dimensional processes, which are rather straightforward and similar to what we covered in Unit 1. And then we'll look at some three-dimensional applications as well. Some of these examples are quite challenging and are complex, unfamiliar in nature. So you will have to pay attention, maybe go back, look back over, and try to rationalize some of the processes that are used. Okay, so the first one is one that we should have seen before. Prove that the diagonals of a rhombus are perpendicular. So if I set up my rhombus, draw my sketch first. Now we do know that with a rhombus, one of those really important properties is that all the side lengths are the same. So if we can say that this is vector A and this is vector B, then this is also vector B and this is also vector A. And we know that the magnitudes of A and B are equivalent. All right, so we're trying to prove that the diagonals are perpendicular. So really my RTP statement is, and I can choose whichever diagonals I want. Let's say this is OABC. We're going to try and prove that OB is perpendicular to AC, which means what we're really trying to do is show that the dot product of OB and AC is equal to 0. So with that in mind, we can now start working forward. So let's look at our left-hand equation, which is this OB dot AC. Now OB, if we want to define it as direction vectors, will be vector A plus vector B. So if we follow that path, A plus B. Dot, if we're looking at AC, then we're going backwards along A, so it's negative A, and then forwards along B, so negative A plus B. Now if we expand this out using distribution law, we get negative A dot A, we get positive A dot B, negative A dot B, and then positive B dot B. Now these two can cancel out, they're the same. And we're left just with negative A dot A plus B dot B. Now remember, when we're looking at the dot product of a vector with itself, we can rewrite that as the magnitude squared. So we're looking at negative magnitude of A squared plus magnitude of B squared, but we know up here that they're equivalent. So because they're equivalent, that we end up with 0, which is our right-hand equation, and we can say that we're pretty happy with that. Okay, so a nice easy proof there. The setup was really important, and this statement of those extra pieces of information at the start was also very important to the solution. All right, so we'll move forward, and now we've got another one that we should have seen before. Prove that the angle subtended by diameter in a circle is a right angle. So I'll start by setting this up. There's a line that goes through the center, and we'll say it goes to A, B, and D. So here's our right angle triangle. Now one thing that we want to use to relate everything here is a radius. So our statement at the start here is saying, well, the magnitude of AC is the same as the magnitude of CB, which is the same as the magnitude of CD, and they're all the radius. Now, because AC and CD are on the diameter, we might say that this is the radius vector, and therefore this one here is negative radius vector. And because we're trying to prove a right angle, we're trying to prove perpendicular, so our RTP statement is going to be that we're trying to show that AB is perpendicular to BD. And that means we're looking to show that AB dot BD is equal to 0. As soon as we've done that, as soon as we've got past that setup stage, this proof is very, very similar to the last one we just did. So AB, let's define that. We can say that's negative R, and we'll probably have to name this one, so let's name this one B. So we have negative R plus B and dot. So to go from B to D, we'll go negative B and then negative R. Now I shouldn't be working like that. I should be saying that I'm focused on the left-hand equation. All right, so let's use distribution law again and expand this out. We've got R dot B and positive R dot R and negative B dot B and negative B dot R. So these two are the same. We can get rid of them. And we're looking at magnitude of R squared, take away magnitude of B squared. Now B, as we showed before, BC or CB is the same as the magnitude of CA, that radius. They're both the radius. So therefore it's equal to 0, which is equal to the right-hand equation. And we can make our final statement. Okay, so two nice straightforward ones, similar to the type of proofs we were looking at last year. Now, this next one is not simple. This next one requires us to use some ratios, and we'll have to determine those ratios and make a couple of logical jumps. So let's set up a triangle. We'll call it OAB. Here's a triangle. We want to prove that the medians are concurrent, and so that means that all the medians meet at the same point. So let's draw in our medians using black. So we'll call this one here X, ratio 1 to 1, because it's a median. We'll draw our ratio here, and we'll call that Y. And then we'll draw our third median, and we'll call that Z. We'll say that they meet in the middle at point M. And we'll have to define some parameters here. So let's say this parameter here is n, and we'll make that 1 take n. Now the reason we do that is n plus 1 take n is equal to 1, so that when we're looking at the ratio, we're not having to deal with fractions. And we'll say this one here is p, and 1 take p for the same reason. Now what we're going to look at doing is look at OM two different ways. So OM and OM. So the first way we're going to follow is a nice simple OM using this line OX. So the first thing that we'll write here is, well, it's n out of 1, so n on 1 of OX. So it's a ratio of the vector OX. Now OX can be defined as well. So OX, I should have earlier stated these. This is vector A, and this is vector B. We'll do everything in terms of the direction vectors A and B. So if we go back now, we can say that OX can be OB plus BX. That means we're looking at vector B. Now BX is just going to be 1/2 of BA. And to go from B to A, we're going to have to go backwards along B and then forwards along A. So it will be negative B plus A. So now we've broken that down to N. We've got B, take 1/2 B, so that means we've got 1/2 B plus 1/2 A. So we end up here with 1/2 N in the A component and 1/2 N in the B direction. So now we need to choose another way. I'm going to say that we'll follow the path OA and then AM. So OA is nice and easy. It's A. AM is going to be P over 1, or P bracket AY. So it's that fraction of AY. And to go from A to Y, then we're going to say that it's negative A plus 1/2 of B. So now we've got A take PA and then plus 1/2 PB. So that gives us 1 take P in the A direction and 1/2 P in the B direction. Now here's a trick. Because these two things are equivalent, they're both OM, then we can equate the directions. So straight from here, we can say that this 1/2 N and this 1 take P is the same. And we can also say that this 1/2 n and 1/2 p is the same. So we've got 1/2 n is equal to 1 take p, and we've got 1/2 n is equal to 1/2 p. So n is equal to p. If we put that back in over here, then that means we end up with 1/2 n is equal to 1 take n. And when we add that n across, we've got 3 on 2, n is equal to 1. If we multiply by the 2 and divide by the 3, we end up with n is 2/3, which follows that p is 2/3. And due to symmetry, if we have n is 2/3, np is 2/3, and it follows that our third ratio, and we never name that, so let's call it r. So we'll say this is r and 1 take r. We'll say that our third ratio is also 2/3. Now this combine tells us that those medians are concurrent. They do have an intersection at what we call the centroid of the triangle. Okay, so that one was a very challenging one. Working with those ratios is always going to be difficult. Making sure that we use that sum of parameters is equal to 1, so we've got a ratio or fraction where 1 is the denominator. It always makes that simpler. Okay, so now we have our last example, parallelepiped, which is basically a 3-dimensional parallelogram, and we're looking to prove that the diagonals of OF and CE bisect each other. So bisect is a little bit easier. That means we're showing that they meet in the middle. So it's like a center intersection. So we'll start by defining. We'll say this is A, so this direction is A, this direction is D, and this direction up here is C. Put in what we're looking for. So we're looking for OF. So here's O and there's F. We're looking for this vector. And our other one is CE. So CE, looking for this vector. So let's start by defining what OF is. So OF is equal to, now we'll go D, so we'll go down this direction, and then we'll go across here, and that will be A, and then we'll go up to F, and that will be C. So OF is D plus A plus C, and when we want to define CE, we'll have to go down against C, so it's negative C, and then we'll go along D, and then we'll go along this DE line here, and that'll be plus A. The easiest way to go about this is to name this middle point. So let's name this middle point M. And similar to the last example, but much easier, we're going to say that we're looking at OM in terms of this diagonal, and we'll also look at OM in terms of this diagonal. And this will be the C diagonal. Right, so let's say OM is equal to, so if we start at O and we're going to M, then we're saying that it's going to be 1/2 of OF. And so that's a nice easy one. 1/2 of OF is going to be 1/2 of A plus 1/2 of C plus 1/2 of D. Now when we look at OM over here, if we can get it to be the exact same thing, then that means that the two diagonals must meet at that bisect point, that what we've assumed is true. So go from O to M via CE, we're going to say that it's OC plus 1/2 of CE. So OC will be C, so we've got C plus 1/2 of CE, which is negative C plus D plus A. We determined that earlier. So we've got C, take away 1/2 C, and that gives us 1/2 C plus 1/2 D plus 1/2 A. Now, as equivalent, then we can say that that bisection is true. So they split directly in half. Now, the second one's a little bit more complex. We're saying let M be the midpoint of CB, so we'll have to get rid of this extra M that I put in, and let N be the midpoint of DE, and we're trying to prove that the midpoint of MN is the point where the diagonals of OF and CE intersect. So we already know this OM, this midpoint, so we're looking to show that if we can find the midpoint of MN from the origin, it should be the same as that OM that we worked out in the previous. Now, obviously, the M's make this a little bit confusing, but I'm sure you can get past that. So let's start by looking at MN. Let's define MN. Go from M to N. We're going to say that it's MC plus CO, MC plus CO. So we've gone across and down. Now we can go OD plus DN. Now MC is negative 1/2 A. CO is negative C. OD is D. And DN will be 1/2 of A. So those two cancel out, and we're just left with MN is D take C. Now, we'll have to rename this middle point, so let's call it X now. So what we want to do is we want to find OX. So if we're trying to find OX, the first thing we're going to do is we'll go from O through to N or M. We'll use M because we've already got the vector Mn. So if we go OC, CM, so we go up to C, we go across to M, and then we want to look at going 1/2 of Mn. So OC is C, CM is 1/2 of A, and then we want to look at 1/2 of Mn, which is our D take C. So we've got C plus 1/2 A plus 1/2 D take 1/2 C. And now we've got 1/2 A, 1/2 C, and 1/2 D. Now that OX is the same as our OM, which means that midpoint of MN does meet at the same point as that intersection between those two diagonals. All right. So those last two examples were really challenging, and I hope that you'll engage with questions of that same difficulty so you can keep on building these skills. The questions that are set are generally the 3-dimensional ones, but if you want to go back and practice some 2-dimensional ones and build your skills, then feel free to do that as well. Just note there is a lot of questions, and I don't expect you to finish all of them. Thank you very much for listening.